Welcome to the Deep Dive. Today, we're going to focus on something that I think is often way more critical than just the average. Because in almost any high-stakes environment, think manufacturing, service delivery, the mean value is really just the start of the story.
It really is. The thing that actually kills efficiency, the thing that kills reliability, is inconsistency.
And that's what we're talking about today.
Yep. And that inconsistency, it has a name. It's the variance of the population. You know, if your assembly line hits the target weight on average, that sounds great. But if the individual packages are all over the place, you're facing huge losses.
Right, from overfilling or, even worse, from underfilling and getting into trouble.
Absolutely. Reputational damage, regulatory fines, you name it.
So our sources for this deep dive give us a fantastic toolkit for testing that very inconsistency. We're getting into statistical inference for population variance, or sigma squared, how to estimate it, and how to formally test it.
And our goal here is to get you comfortable with two really critical statistical distributions, the chi-square and the F distribution. These are the specialized keys that let us answer the big questions.
Like, is my process stable?
Or, are these two suppliers I'm looking at actually different in terms of their consistency?
Okay, let's start with that classic example from the sources. The liquid detergent filling machine. So the machine's average fill is a perfect 16 ounces. Great.
It sounds great. But it's not if the variance is all over the map. If the machine isn't precise, a huge number of bottles are going to be severely overfilled. That's just pure profit you're pouring down the drain.
And on the flip side, you have underfilled bottles, which, like you said, can expose the company to all sorts of legal trouble. So that gap, the one between the perfect average and the sloppy reality, that's the variance we need to get a handle on.
That's the one we need to quantify.
Okay, let's unpack this a bit. If variance is our target, we can't just use the standard Z or T distributions we'd use for means. So why do we need something new here?
Well, it's because variance, sigma squared, is just fundamentally different. It's calculated with squared numbers, which means it can never be negative. It always has to be 0 or positive.
Okay.
And its distribution is usually not symmetric like the normal curve. It's often skewed to the right. So we need a distribution that, you know, lives in that same space, that non-negative asymmetrical space.
And that is the chi-square distribution.
That's where the chi-square distribution, chi-squared, comes in. It's our primary tool for dealing with a single population's variance.
So let's look at its first job, interval estimation. We want to find a range, right? A range of all the reasonable values for our population's variance based on a small sample.
Exactly. This is so critical for quality control. You don't just want one number, one estimate. You want to be able to say with, say, 95% confidence that the true actual variance of your entire process falls between these two specific boundaries.
Let's go back to the detergent. We take a sample of, say, 20 containers, so N equals 20, and the sample variance, C squared, comes out to be 0.00025.
Okay, so with a sample size of 20, we have 19 degrees of freedom. We use the chi-square table to find the critical values that kind of carve out that middle 95% of the curve.
And after running the numbers through the formula,
the sources tell us the resulting 95% confidence interval for the population variance, sigma squared, is between 0.0014 and 0.0053.
Now, here's the part that you can actually use. I mean, nobody manages a factory floor based on variance. Those numbers are abstract. We care about the standard deviation.
Right.
So what happens when we just take the square root of that range?
It becomes crystal clear. The standard deviation interval is between 0.0380 and 0.0730. And that is a tangible insight. You can go to your team and say, look, we are 95% confident our process variability is locked somewhere between these two numbers.
That quantifies your risk. You know exactly what you're dealing with.
Precisely.
Okay, so knowing the range is great, but sometimes you just need a clear yes or no from management. That's where we get into formal hypothesis testing, still using that chi-square distribution.
Yep. And for any hypothesis test, we need a yardstick, a standard of measurement. We call it the test statistic. For variance, it's chi-square equals N1 times the sample variance, all divided by the hypothesized variance.
It's basically a measure of how far our sample evidence is from what we claimed was true.
That's a perfect way to put it.
So let's run through a scenario with real stakes. The St. Louis Metro Bus Company, they've promised reliability, so they set a policy. The arrival time variance has to be 4 minutes or less. If it's higher, their schedules are a mess, and they could lose their contract.
So this is a classic right-tailed test. They only really care if the variation is too much.
Right, they're not worried if it's too low.
No, low variance is great. So our null hypothesis, H0, assumes everything's fine. The variance is less than or equal to 4. The alternative, HA, is that they have a problem. The variance is greater than 4. And let's set our risk tolerance, alpha, at 0.05.
So the company tracks 24 bus arrivals, and they find a sample variance, squared, of 4.9. A manager sees that 4.9 and, immediately starts to panic, right? Because it's higher than the target of 4.
Right. Is that panic justified? That's the exact question we have to answer. So we take that 4.9, the sample size of 24, the hypothesized variance of 4.0, and we plug it all into our formula.
And what does the chi-square test statistic come out to be?
It comes out to 28.18.
Okay, so 28.18, that's our measure. Is that number big enough to be alarming? When we compare it to the critical threshold for a 5% risk level, what do we see?
We see that 28.18 does not cross that line. It doesn't meet the threshold. The gap between the 4.9 we saw in the sample and the 4.0 target, it's just not wide enough to be statistically significant.
So the conclusion for management is we fail to reject the null hypothesis.
Exactly. That little bump to 4.9 wasn't a real crisis. It was most likely just random fluctuation in that specific sample. There's no statistical evidence to claim the whole schedule is unstable.
That saves them from freaking out and trying to fix a process that isn't statistically broken.
That is the power of using evidence, yeah.
Okay, so that handles one population. But in the real world, we're always comparing things, right? 2 production shifts, 2 different suppliers. What tool do we pull out when we need to compare the consistency of 2 different groups?
That is the perfect transition. That is when we move to the F-test. When you're comparing 2 independent, normally distributed population variances, the F-test is the standard.
And its structure is a little different because it's a ratio. The test statistic is just the first sample variance divided by the second one.
That's right. F equals S1 squared over S2 squared. And there's a crucial little rule here for setting it up. You always designate the population with the larger sample variance as population 1. You put the bigger number in the numerator.
Oh, interesting. Why?
It just ensures the F statistic is always 1 or greater, which makes using the F tables and the decision rules way simpler.
Got it. And the F distribution, it has 2 different degrees of freedom, right? One for the numerator and one for the denominator.
Exactly. And our null hypothesis, H0, is just that the 2 populations are equally consistent, that their variances are equal.
Let's look at the Dulles County school bus contract example. They have to choose between 2 companies, Milbank and Gulf Park, based on reliability. So they're running a test to see if their consistency differs at all.
A 2-tailed test. And they set their alpha at 10%.
The data comes in. Milbank's sample had a variance of 48 from 26 trips. Gulf Park's was 20 from 16 trips. So since 48 is bigger, Milbank is population 1.
Right. So we calculate our F statistic. It's just 48 divided by 20.
Which is 2.4.
Just 0.40.
Yeah.
And our degrees of freedom are 25 for the numerator and 15 for the denominator.
Now, because this is a 2-tailed test with an alpha of 10%, we're looking for the critical cutoff in the table that corresponds to alpha divided by 2, which is 0.05.
We check the F table with those degrees of freedom, and we find that critical value. And what we discover is that our calculated F, our 2.4 euro, is greater than that cutoff. It's in the rejection region.
So we have to reject the null hypothesis.
We do.
And the implication for Dulles County is huge. The data provides statistically significant evidence that these 2 bus companies do not have equal arrival time variances.
Their consistency levels are genuinely different. The county can't just treat them as equally reliable suppliers. It's not just an anecdote anymore.
It's a statistical confirmation.
Yep. If they award the contract to the company with the higher variance, they are knowingly choosing a more erratic, less reliable service.
This has been a really compelling deep dive into quantifying risk and consistency. We've shown pretty clearly that just looking at the mean can be a really dangerous shortcut.
We've armed you with the essential tools, The chi-square distribution for a single population's variance, and the F-test for comparing the consistency between 2 of them.
These tests let people move from just guessing about stability to actually confirming it with hard evidence.
They do more than just calculate a number. They quantify your risk. They tell you the true vulnerability you have to, say, overfilling, or the real difference in reliability between 2 vendors.
The so what here is that this knowledge lets you control the scatter, the variability, and that's often way more impactful on your bottom line than tiny shifts in the average.
It really is.
Which brings us to our final provocative thought for you to consider. The next time you hear a news report or a memo at work about an average improvement, say, the average time to process a loan went down. The most important follow-up question might not be, how much did the average change? It might be, how much did the variance change?
Yeah.
Managing that spread could be the real key to excellence.
Keep looking beyond the mean.
Until next time, keep digging into the data.